dialing in today. Happy Friday, first off, and yeah, just wanted to have a discussion today on AC versus DC coupling. This is a topic that, in spite of being several years old, has people firmly entrenched on one side or the other, and continues to be an ongoing topic around solar plus storage. And I wanted to perhaps introduce a different way of thinking about this. Perhaps not different and new, but maybe new to you. So that said, let's get started. As Caitlin pointed out, we like to do a survey at the end. I appreciate all the feedback we get, good, bad, or otherwise. It helps me and my team develop better content for you and know what resonated, what didn't, what needs clarification, etc. So please take a moment at the end there. And as Caitlin pointed out as well, if you've got any questions, type them into the chat function. I'll do my best to answer as many as come in as thorough and complete a manner as I can. That said, I'm not a professional engineer, so if you stump me, I'm going to have to reach out to my team and get back to you. But that having been said, let's get started. So I like to start these webinars by covering what we're going to talk about today, maybe kind of frame the discussion a little bit. So spend a little time on terms and definitions, a brief background on kind of how we got to where we are and why there's two architectures or topologies out there. A little bit of the justification or rationale around DC coupling, around AC coupling, talk about some side considerations that you probably thought about before and maybe have put you on one side of the fence or the other. Talk about different products and how it can be used in the two different applications, and then finally some questions and answers. So that's our storyboard for the day, and let's get into it. So what I was trying to frame up for you guys today was thinking about AC and DC coupling not as good and bad and as a kind of a dichotomy of one versus the other, but think about two different tools. So the analogy here, and I take this from a former coworker that a really smart guy by the name of Deval Shaw. He came up with this analogy, or at least that's the first place that I saw it implemented. And from his perspective, think about, don't think about the best or the worst, but think about what's right for the application. And his analogy was drivetrains and automobiles. So on the left here, we've got front engine, front wheel drive car. On the right, we've got a front engine, rear wheel drive car. So maybe this is a bad example because similar to AC versus DC coupling, people are typically in one camp or the other. But I think if you're trying to evaluate what's the best drivetrain for a car, the answer is, well, it depends. What are you trying to do? Or as a guy in my team would say, what's the job to be done? So there's no hands down best case. It really depends on what you're trying to get done. In this example, there's lots of factors that are going to define how you make your choice. What's the use case? Are you driving around and commuting in the city? Are you racing? Are you going off-road with your vehicle? How are you evaluating performance? Is it stability? Is it traction? Is it lap time? How easy is the maintenance? How cost-effective is it? How reliable? What does the drivetrain decision do to the compactness or weight of the car? Lots of different things that go into evaluating if front-wheel drive front engine is better than front engine rear-wheel drive. So me personally, I've almost exclusively driven front-wheel drive cars, but I'm really looking forward to the possibility of owning a rear-wheel drive car in the near future and having something a little more fun to drive around. I've gone front-wheel drive in the past just because it's been more cost-effective. Those cars typically get better fuel economy, and I've got a long commute. So just a little analogy there to perhaps frame our discussion. So some definitions, and these are sometimes tricky. There's not global standards on how we define DC versus AC coupling. These are my functional descriptions that I use. DC coupled or DC coupling. In my lexicon, that refers to the array being introduced to the system, so the power from the array hitting the system on the DC side of the hybrid or battery inverter. And for each of these, we'll have some block diagrams later to kind of illustrate this. So typically the power, the array wattage, if you will, is introduced to the system via a charge controller to the DC bus, and then the battery inverter is going to make decisions on what to do with that power. In an AC coupled or AC coupling, you're introducing that PV wattage to the system on the AC side of the hybrid or battery inverter, typically via a PV inverter. So, fairly well understood descriptions. I think at a high level, we all kind of understand what that means. To further complicate the issue, though, in the past couple of years, we've seen a number of, I call them AC batteries, that have been introduced. So these are standalone batteries. I would say obviously, but I don't think that's the case. There are no battery chemistries which store watt hours in an AC fashion. Every type of chemical storage is by definition direct current. The difference occurs when inside that box that you're ordering from Tesla or someone else, there's an onboard inverter, so that when you connect it, the output of that device is already AC. So I don't have any block diagrams here, but if you're interested, we can send you some. These AC battery configurations are really, they're not AC coupled, they're not DC coupled. It's kind of a beast unto itself. So I like to distinguish that, because in conversations I hear a lot about, well, Tesla is AC coupled, and in my lexicon, in my view of the world, it's not. It's something different. So now that we've got the definitions out of the way, I wanted to talk a little bit about kind of where we come from as an industry and why DC coupling has been the most prevalent to date. And I won't belabor this slide too much, but essentially what we're looking at is kind of the evolution of charge controllers from the early days of relay-based charge controllers that had a high voltage disconnect and a low voltage disconnect. And when the conditions were met on the array voltage, the relay closed and directed power towards the battery. And when the battery voltage rose to a certain point, the relay would open up and you wouldn't be charging anymore. From there, we evolved to a pulse width modulated PWM charge controller that now introduced the possibility of bulk and float charging. So basically varying the voltage that the battery would see based on the wattage that the battery would see from the array based on the current voltage state of the battery. The final evolution, an MPPT charge controller, was really revolutionary for a couple of reasons. One, it allowed the array to operate more efficiently at an MPPT, so to harvest more wattage, but also, perhaps more importantly, allowed you to operate an array at a different voltage than, let's say, the battery. So no longer were we restricted to 48 volt arrays for 48 volt batteries and 12 volt arrays for 12 volt batteries, but now we could move to much higher array voltage and see some increased efficiency. So having come from that background, I think it's obvious why the initial inverter systems that we saw in the market were DC coupled. Charge controllers were prevalent before inverters became cost effective, and that's just kind of how the industry evolved. So I've got here a really simple block diagram of a typical off-grid DC coupled system. I'd say typical. Obviously, we've drawn this up with a Radian, but any of the major brands would apply here. We've got an array of 3 60-cell modules, a FlexMax 80 charge controller. The MPPT charge controller is going to modulate the voltage of this array to harvest the appropriate amount of power for the rest of the system. And I say appropriate amount of power because it's going to raise or lower the voltage that the array sees based on what's being called for from the battery. As the battery, quote unquote, fills up, the terminal voltage is going to rise, and the array is going to see less potential to push power out. As the battery voltage drops, the MPPT charge controller is going to lower that voltage, create more of a potential, and try to harvest more out of that array. We've got this drawn up with the appropriate kind of power flows here, so you can see the DC from the battery to the Radian is bidirectional. So it can both harvest power from the battery bank to be inverted for loads to this AC output, or in the case of this generator running, the generator can run, can provide AC power to the radian. Any excess power can then be converted back to DC and put back into the battery. So pretty simple stuff. And I won't belabor that point. We've got another example here of a Schneider electric system with an SW and an MPPT80. This one happens to be grid-tied. So you see you've got a unilateral, if you will, power flow from the grid to the inverter. There's obscured here, but there's relays inside this inverter that will allow that power to pass through to loads in the home. And then, of course, we can supplement that by inverting from battery or inverting from PV. This is not a bidirectional power flow because the SW has some control circuitry that doesn't let you sell back to the grid. So it's a little unique from the Radian or from the XW or from some of the other products out there. And I've got here a couple sample systems. This is an LTAC system in, I believe, Laramie, Wyoming. Array up on the roof. Lots of energy storage for extended extended outages. I believe this is an FP2 with 2 FlexMax 60 charge controllers. So fairly simple off-grid system, provides lots of autonomy for extended outages. And because he's got the array kind of co-located with the power electronics equipment, it's a DC system. I don't believe this one is grid-tied, so again, fairly simple. I've got another one that's along the same lines here, a little bit larger in scale. So this is a 3XW system with a total of 8 NPPT charge controllers, and boy, I don't know how much energy storage here, but so sufficient to say quite a bit of energy storage. So along the same lines of what the previous system was trying to accomplish, harvest the power, co-locate the equipment. We're not grid tying, and we've just got a lot more storage because I deduce this by the number of inverters, a lot more loads, and a lot more energy requirements. So those are some really simple DC coupled systems that we see out in the market. And while the products have changed and while the sizes and the capabilities have increased, the general architecture of the DC coupled system really hasn't changed significantly in, I don't know, maybe the past 15 years. So we've covered DC coupled. I want to take a minute and start to talk about AC coupling. So I've got here an example system of a Sunny Island, and I believe this is a SunPower brand labeled Sunny Boy from a few years ago. And the Sunny Island product, in my view of the market, really kicked off the desire and the approachability of AC coupling. And this was for many years a very elegant and very efficient system. So here on the right, we've got a block diagram similar to what we saw in DC coupling. You've got an array. Note here you've got a much longer string. So not having counted them, I believe this is, well, I'm going to count them, 2, 4, 6, 8, 10, 12 modules in a string. We've got a disconnect. We've got a grid tie inverter. You'll see this referred to as a grid tie inverter or a PV inverter. I like the term PV inverter because there are battery inverters that are grid tied. So in order to avoid misclarification, I typically refer to that as a PV inverter. A protected load subpanel. Protected loads. Notice this is a one-way feed here. If we had a generator, this would be bidirectional. You've got a bidirectional flow here between the protected load subpanel and the battery inverter. The battery inverter connected, of course, to the DC bus with the battery bank. Notice again, this is bidirectional, so it can invert from battery, or it can flow the other way and charge the batteries via the utility service or the PV inverter. An AC disconnect, utility service panel, utility meter. So this is a fairly standard AC coupled system. I've got another diagram here This is probably going to appear for most of you out there over the internet as an eye chart, but I'll try to illustrate some of the higher points here. So we've got our this is an older diagram. So this is an Outback Radian 8048, GS 8048. Now you would see this labeled as a GS 8048A-01, but for all intents and purposes here, the functionality is the same. We've got our GSLC load center, which serves as kind of, operational hub between the critical load panel, the main service panel on the AC side, as well as on the DC side, your wiring panel for the breakers needed for your battery bank, as well as the AC breakers for possible generator, and bringing in the PV array here. So you see array, string combiner, PV inverter, coming in here and landing on this remote operated circuit breaker. This ROCB, not presently available. We're currently recommending, my team is currently recommending, if you're interested in this kind of system, to use a relay rather than a remote operated circuit breaker. We feel that there's, I think, higher durability and better lifetime out of kind of standard over-the-shelf relays rather than remote operated circuit breakers. But the functionality, except for the overcurrent protection, of course, is essentially the same. So, what's the rationale behind DC coupling? And please forgive me, but I've really tried to simplify this as much as possible, as much for my edification as for yours. So, pros. Typically, we see better communication between inverters and I'll call PV harvesting. So, if you're using components of one brand, there's typically communication between the battery inverter and the charge controller. If they're not of the same brand, they can effectively communicate via moving the DC bus voltage up and down. I'll say more efficient for non-concurrent loads. So we'll talk about this in a few slides, but I think this is a key point. When you're storing energy for later, you're saving yourself a conversion cycle. And I've got some diagrams. We'll get into that a little bit later. The last point here in pros is simply a wider array, pun intended, of available equipment and pre-wired solutions. So simply put, more product to choose from to meet this application. What are the cons of DC coupling? Well, I think first and foremost, the wiring can be very expensive. If you're dealing with large systems or with systems where the equipment is not co-located, so if you've got if you've got an array that's out in the sun at the top of the hill and all of your power equipment needs to be at the bottom of the hill near the loads, wiring is going to cost a ton. Obviously because of the length, and then just because of the voltage at which the connection between, call it the PV and the battery inverter is happening. So if you're in a DC coupled system, you're running cabling between that charge controller and that inverter at a 48 volt level. Ohm's law being what it is, the conductors you're going to need to size for, call it 6,000 watts at 48 volt are going to be a lot thicker, a lot more expensive than they would be in an AC coupled system, and we'll get into that in a second. Another con here being less efficient during concurrent loads. So if you've got a system and most of your usage is during, call it insulated or times when your array is producing power, this can be less efficient for those types of loads. This should actually be a pro. So this ended up in the wrong column, but greater flexibility on sizing the inverter versus the array versus the storage. So in a DC coupled system, it's you've got more options, let's say, for having different sized arrays and inverters and storage. A lot less flexibility on the AC coupled side. So before we get into the pros and cons of AC coupling, I wanted to clarify a little bit in a little bit more detail what I meant about concurrent loads and round trip efficiencies. So let's think about two drastically different load profiles. We've got here in the top left an off-grid home in Wisconsin. So loads here in blue, generator power being this kind of gold color, and total MPPT power or array power in green. So for the most part, except when this generator is kicking on, we see that loads are pretty much in sync with what we're able to do via production of the array. So the sun comes up in the morning, people wake up, they're turning some things on, they're running some loads, they go through their kind of daily behavior. We've got a spike here around midday that I'm not sure what that is. Maybe it's a tea kettle, maybe it's the air conditioner, I'm not sure. Loads drop, and you see here the generator kicks on. Loads drop off and they remain relatively stable through late afternoon. We're able to harvest a lot of energy and put that into the storage. Then you see kind of a typical evening spike where we're fixing dinner, doing dishes, etc., and then we go into kind of steady state evening. So this is an example where really the loads are pretty concurrent. They're occurring at essentially the same time as our production. On the other hand, this case down here is this is a rural electrification project in Indonesia, but I think similar projects occur everywhere in the world where our peak loads are actually occurring later in the evening, so essentially after the sun has gone down. So in an area where most of our loads are lighting and home appliances, this would be fairly standard. So this one is an example where essentially the building or the site is unoccupied during the day, or the loads are not electrical in nature. So in this instance, you've got non-concurrent loads. Well, what does that mean for the system, and why do we care? Got a couple cases here where we want to look at round trip efficiency. So generally speaking, DC coupled more efficient when storing energy for off-peak hours. Why is that? Well, when we're storing energy, we've only got one conversion stage. We're bringing power in from the array, we're running it through the MPPT charge controller, and it's going into the batteries. So for simplicity's sake, I haven't included wire losses. I've assumed 100% efficiency on the kind of storage into the battery. So one conversion cycle, we're only limited by the efficiency of the charge controller, so call it 96% efficient. In a two-stage conversion though, so when we're consuming that power during production times, we've got two stages. So we're bringing it from the array to the MPPT charge controller, into the batteries, then back out of the batteries to the battery inverter, and then to the loads. So the limiting factor here is A, you've got two stages of conversion, and B, your battery inverter is going to be a lot less efficient at inverting from DC than a PV inverter would be. So math being what it is, two stages, a battery inverter that's much less efficient than an MPPT charge controller, we've got a round trip efficiency of, call it 88%. So you see here 96% versus 88, much more efficient when storing for later usage. In an AC coupled system, when we're talking about storing energy for later, we've got two stages, from the DC array to the PV inverter. So you see here that the PV inverter is going to be more efficient than an MPPT charge controller, as we would expect. We've got a not a conversion, but a kind of a pass-through to the battery inverter, and we've got some losses there. Back into the batteries, 88.2%. So this 91%, really what that's speaking to is the efficiency of the charger on board the inverter. So the charge cycle in a battery inverter is typically going to be less efficient than a similar charge cycle from an MPPT charge controller. So a round trip efficiency of storage of 88%. Consuming single stage conversion, this is as simple and as efficient as an AC coupled system can get. We've got wattage from the array to the PV inverter, 97% efficient. And these slides are a few years old, so that number has risen to 98.5%. Out to the AC loads, call it 97% for the purposes of this exercise. In both cases, consuming energy from storage only, So in both cases where we've stored the energy and we're using it, we're bringing it from the battery through the battery inverter, 92% to support the loads. That functions 92% efficient. So that's a lot of numbers, and I went through that really quickly. What does that all mean? I think a possible tendency would be to say, well, I'm 88% here and I'm 96% there. I average those and I get to, 92. And I average these and I get to 92.5. What's the difference? Well, you can't average them. You've really got to think about, in each of these scenarios, what's your proportion? How often are you in each of these cases? In a DC coupled system, how often are you storing for later versus consuming at the same time? In an AC coupled system, how often are you consuming versus storing? So I go back to this slide, and in this instance where loads are concurrent, you're probably better off going with an AC coupled system, because you're going to be in a single stage conversion more often. You're going to be inverting and powering loads more often than you are going through that two-stage of inverting, charging from charging the battery from AC and storing it for later. In the second case, where your loads are non-concurrent, you're going to be in a single-stage conversion more often. You're going to be charging the battery via single-stage conversion more often than you're going to be powering concurrent loads. So I'm going to leave it there for a second, and hopefully that hopefully that kind of triggers some thoughts about the difference in conversion between the two topologies. And that's before we've talked about any of the other considerations that we're going to get to in a minute. But really think about, when's your production, when's your loads, and how well do they line up? Now let's talk about why AC couple. So on the other side, kind of belabored this point now, but more efficient harvest and inversion. So a modern PV inverter is going to be much more efficient for powering concurrent loads. We touched upon this point already, but higher voltage, so higher DC bus voltage between, call it the array, all the way through to the battery inverter. It's going to be wiring savings. So I'm sure lots of you guys have done projects like this where you've looked at this and realized, holy cow, there's a lot of savings if I can figure out A, how to raise the voltage, and B, how to get it to an AC run rather than a low voltage or high voltage DC run. Really what I see in talking to customers out there is, they might get called back to a system they installed in the past. Customer wants to know why, when the power goes out in the neighborhood or the transformer goes down, why they don't have power, and you're looking at a retrofit. So when the equipment's already installed, it's really tough to tell a customer, I've got to take some of that off, I've got to rewire, there's a whole lot more work involved, and I've got to add a battery inverter and a battery bank, etc. And I think there's just there's a behavioral element there of, I think the roots of our industry are rooted in in conservation and doing the right thing, in taking a bunch of equipment off the wall and putting it in back into storage or in a landfill just feels wrong in a lot of senses. So completely understand that that predilection. I'll add in the pro side here, if curtailment is enabled, can be a very elegant solution. So you get kind of if you've got a PV inverter that's capable of doing curtailment, it can be a really elegant solution. On the con side, and we're going to get into this in a second, but uncontrolled charge currents. Try saying that 3 times fast. Uncontrolled charge currents when islanded if curtailment is not equipped. So that's a really long-winded way of saying, if you've got an AC coupled system and the system becomes islanded, either because it's off-grid, which is not recommended, but say the grid goes down or you make a conscious decision to island yourself, you can have some really high charge currents into a battery because the components don't speak to each other. And we'll get to that in a second. Fewer approved options for the storage inverter and really the PV inverter. So as opposed to the DC coupled side of the fence, where lot more equipment available, and approved usage with a variety of kind of mixing and matching of brands. There's just, frankly, there's less options out there for approved hardware. And those of you that have been around the industry for a while have heard probably some horror stories of trying to troubleshoot an AC coupled system or trying to get support and being told, hey, we're sorry, that's not a supported application. Never a pleasant experience, and unfortunately, a lot of us found out about that after the fact. So, really the takeaway there is encourage you to do your homework and, talk to people on my team, talk to manufacturers, find out what's supported before, before you make purchase decisions, before you go out and design and install a project. And I'll say here, reduce flexibility on system sizing. We'll get into that as well. But what you see from a lot of manufacturers of battery inverters who do support this application is they support it with a particular set of circumstances on, call it matching the ratings of the PV inverter to the battery inverter. So a lot there, and hopefully in the next slide I can explain kind of some of these pros and cons in an AC coupled system. So this comes courtesy of our friends over at Schneider Electric. This is a functional schematic of an XW Plus in a grid-tied AC coupled application. So we've got a grid, we've got a one-way flow. Call it one-way. That could be bidirectional if you've got net metering approved. To your main panel, we've got a one-way power flow. Again, that could be two-way to the XW Plus. We've got a line here to the relays in the XW Plus. We've got pass-through relays that, when closed, will allow power to flow through from the main panel to the AC subpanel. We've got a SMA Sunny Boy from a few years ago. We've got an array. We've got an AC subpanel. And here's kind of a functional schematic of what's going on in the inverter. So at a high level, relatively simple AC coupled application. And when this relay is closed and we've got power available, the PV inverter will, let me take a pause there because I think it's important to describe the goal in life of a PV inverter versus a charge controller. So the goal in life, if you will, of a PV inverter is to harvest as much power as electrically possible from this array and dump it out onto whatever qualified grid it sees. So if these relays are closed, it's going to sync to the grid that's supplied from the utility grid, provided it falls within the qualifications as established by UL 1741 or 1741 SA. So if the inverter sees a qualified grid, great. I'm going to do my 5-minute count up, make sure that the grid remains qualified, and then I'm going to inject as much current as possible that I can harvest from the array. And engineers being what they are, they've gotten really efficient devices that harvest a ton of power and will inject as much current as they can without exceeding their ratings or tripping circuit breakers. So that's the goal in life, if you will, of a PV inverter. Going back a few slides and thinking about what does a charge controller do, the charge controller is going to harvest what I call the right amount of power to service the battery or service the DC bus. So what does that mean? It's going to look to the voltage on the DC bus to make decisions about how much power to harvest, knowing, because you've programmed it as such, what type of battery you have, how many charge amps it can supply, and having essentially a 3-stage charge profile for that battery type to know that A, I'm in bulk, B, I'm in float, A, I'm in bulk, B, I'm in absorbed, C, I'm in float, and knowing how to tailor the wattage that it's harvesting from the array to supply the right amount of power to that battery. The PV inverter, coming back to that, doesn't make those decisions. Again, it's trying to supply as much power as possible, which in a net metered environment, hey, that's great. This is energy that I'm not going to have to pay for later. The grid's willing to take it. I'm going to keep shoving power onto the grid. The problem can occur now when we talk about UL 1741SA if it sees that grid voltage or grid frequency start to rise, it's going to start to pull back and curtail power, which, you know, from a smart grid point of view is exactly what it wants to do. Now we've got an example where we're looking at the connection, call it the connection between the grid and the main is no longer established. So this could be an outage, this could be a conscious decision to island the system, or, you know, in an extreme case, maybe this grid never existed and we're dealing with an off-grid system. So now what happens? We're in backup mode. The PV inverter, as long as it sees a qualified AC grid, is going to continue to shove current in synchronous fashion to that grid, as long as the voltage and frequency remain in kind of the predetermined standards as defined by UL 1741 or kind of whatever you've programmed into your inverter. And I say that because some PV inverters out there can do what we call off-grid mode, where they're going to take directions and commands as interpreted by frequency and voltage. So we're in backup mode. The system is continuing to produce power. In this case, the XW plus is inverting from backup from battery to create an AC grid that the PV inverter is syncing to and injecting power onto. So hey, that sounds great. Well, let me describe a scenario for you. It's quote unquote high noon. Lots of solar resource out there available, but you know, for whatever reason, there's very little load. So what happens in that state? PV inverter is going to continue to inject power. The battery is, you know, it's noon. So let's assume we've used some of the battery overnight to power loads. The battery starts to, you know, it goes through bulk, it goes through absorb, it's hitting float. So the XW plus is saying, hey, my battery's filling up, and I've still got all this. I've got an AC grid that's. Sorry, let me take a moment to make sure that this is clear and I describe it accurately. The battery's filling up. I've got excess power on this AC bus. Excess power because I've got minimal loads, being that it's noon. What do? The power has to go somewhere. I can't just, you know, turn it into heat. My choices are the choices on the XW plus or the Radian or whatever you have are very limited. So this is what I call an uncontrolled charge current, where there's excess power on the AC bus. The battery inverter doesn't want to put it into the battery. If it can't curtail the inverter, and we'll get to that in a second, if it can't curtail the inverter, it's got no choice but to raise the AC voltage and turn this inverter off. Why is that a bad thing? Well, if you're doing that once or twice a day and you're turning that inverter on and off, it's not a very elegant way to do it, but it's probably manageable. And I say it's not a very elegant way to do it because this being a PV inverter, it still has to respect the rules of 1741. And when the grid requalifies, it's got to count up, you know, 5 minutes and then start producing power again. So it's a very lumpy way of providing wattage to this application. The other thing that you typically see in these types of applications where you've AC coupled is the battery is usually not large enough to control those uncontrolled charge currents and to ride through the 5+ minutes of startup again. So I'm an anecdote kind of guy, and I'll explain a system that I worked with a number of years ago, where this was a solar decathlon home. If you're familiar with solar decathlon, it's a competition where college students get together and design really efficient solar powered homes. This one was built and engineered by the University of Tennessee, and eager innovators that they are, they wanted to be able to take this home on the road and show the people of Tennessee, what they did. To be able to do that, they had a 10 kilowatt array that had been installed on the house for the purposes of the competition. They knew all of the places they wanted to take it wouldn't have an AC connection for them to sync up to. So they installed a battery inverter and a very small battery bank. And what would happen, they'd get the house on site, they'd set it up, they'd turn on some lights and things, and in the day, the array would start to produce power. And if the loads were not sufficient, the battery inverter would fill up the batteries, and this being a very small battery bank, the battery would fill up very quickly, and the battery inverter would then turn off the array. Well, this being a very small battery bank, the voltage would drop very quickly as loads were being used, and it would try to turn the PV inverter back on. PV inverter having to do the 5-minute count up once the grid was qualified. Sometimes there was enough battery to power the loads for those 5 minutes, and sometimes there weren't. So the analogy I came up with was, it's kind of like trying to fill a kiddie pool with a fire hose. You've got way too much wattage and current for the battery that you got sized. So the options for this student project were buy a bunch more battery and create a bigger pool to dump, this fire hose of water back into, or find a smaller hose. This being a student project, they didn't have a ton of money and they didn't really have anywhere else in the house to put more battery. What they did is they took one of the PV inverters offline and they kind of downgraded the system to a 5 kW system. So this is not an unheard of event when AC coupling, where your PV inverter didn't necessarily line up with the wattage of the battery inverter. B, they probably didn't have enough battery. They had uncontrolled charge currents. They didn't have a way of curtailing the PV inverter. Their hearts were in the right places, but it was really not the right application. The best thing to do from the get-go probably would have been to install a high voltage charge controller, so that they could still get full array power, but that the battery inverter could tell the charge controllers how much to harvest and how much not to harvest. We've seen a number of a number of PV inverters come to market that have the capability of doing curtailment. Typically, this is done via either communication over RS-485 or a 0 to 12 or 0 to 24 volt signal via an aux relay from the battery inverter. There's a variety of ways to do it, but if you are locked in on an AC coupled system and you've got some of these unique circumstances where you can't add more battery, or you're going to be islanded a high percentage of the time, trying to find an AC coupled system that will curtail is probably a best practice for you. So that was a really long-winded way of me getting to system considerations. So again, going back to, these are two tools in your toolbox, and there's no kind of one-size-fits-all best answer. What are some considerations you've got to take into account when deciding, AC coupled versus DC coupled, or simply how will I do AC coupled? The first being, what's the application? What are you trying to do? Is this a system for backup? Is it a system for self-consumption where you're trying to do rate arbitrage or deal with demand charges? Or is it a pure off-grid system? For me, sitting on my soapbox, I would not recommend AC coupled for off-grid unless you've got a good way of curtailing the PV inverter and you've got plenty of battery. I would hope that an off-grid system will have plenty of battery done, based on a thorough load study, but as we've seen, that's not always the case, frankly. Second will be battery type. Will the chemistry support high charge currents when the system is islanded? Believe it or not, there are some lithium-ion chemistries out there that don't like high charge currents. Some of the solutions we've seen out there in the market have onboard circuit breakers that will trip when you see these uncontrolled charge currents from an AC coupled system where the power's frankly got nowhere to go. So in that instance we talked about a few slides ago, when the system islands and the loads are much lower than the PV array is producing, even when you've got a curtailment-enabled solution, the PV inverter cannot respond instantaneously, and that current has to go somewhere. And in most cases, it's going to try to go into the battery. If that trips the breaker in the battery, you've got a battery you've then got to go manually turn back on again, which is never a good thing in terms of customer satisfaction. Sizing rules. So the ratio of PV inverter to battery inverter. These are going to be recommendations you're going to see from your battery inverter. And what they're trying to get at is trying to deal primarily with point number 2 on here. How do you control the charge currents? How do you make sure that the relays on the battery inverter are not overloaded? If you've got a 12 kilowatt array on a 12 kW, well, I don't know of many 12 kW inverters anymore, but 12 kilowatt array on a 10 kilowatt PV inverter coupled to a 4,000 watt battery inverter, the relays simply aren't rated for that. So, takeaway here is always check with your manufacturer on the recommended sizing of PV inverter to battery inverter. Next consideration is location of array versus power equipment. Is it co-located? Are you within short distances, or are long runs required? As we talked about, if you're dealing with long runs, you really might want to reach for that AC coupled tool in your toolbox. Finally, warranty of PV inverter when AC coupling. You've got to read the fine print. You've got to find out if it's a supported application. The worst thing you could do would be to design a really nice AC coupled PV system, and you realize that the relays have worn out in the PV inverter, and when you mention that it's AC coupled, they tell you it's not supported and your warranty claim is denied. That's a really expensive problem. So, read the fine print. Sometimes it is better off to take that PV inverter off the wall, install a charge controller, rewire the array, or do a high voltage charge controller, and maybe you've got a PV inverter for your next project, or weekend cabin, etc. So I throw in here as well a slide on, this is maybe a poor choice of words, but large hybrid systems. So sometimes the best tool of your toolbox is actually a combination of 2 tools. If you've got a large system and you've got, you feel that you've done a thorough load study and you've got a means of sizing the system via 2 different architectures, this can sometimes be kind of the best of both worlds. So in this system, we've got an array feeding a PV inverter, feeding a subpanel. We've got an array feeding a charge controller, feeding a battery, feeding a battery inverter. Maybe you've got a generator, maybe you don't. Maybe you've got a grid input, maybe you don't. But this can be a very effective way of providing a really effective conversion cycle for concurrent loads via the PV inverter, providing efficient storage for non-concurrent loads, and really sizing the array to the 2 different types of loads. If you're interested in this type of system, by all means reach out. I've got people on my team that can help you engineer it. It's really incumbent on the installer to do the homework, do the math on when are the loads occurring, what are the loads in terms of kWh and kW, and how do you size these 2 properly. What's not indicated on this diagram is, in my opinion, you typically want to have a relay between the subpanel and the PV inverter, so that if this PV inverter can't take curtailment decisions, that you've got a way of turning it off and still supplying this subpanel with power. You can, of course, with these battery inverters, kind of connect and disconnect this AC output, but then your subpanel is not backed up. So perhaps not the best way of laying this out, and I apologize for not having designed this in a better way. But suffice it to say that there's great ways of having your cake and eating it too when it comes to DC and AC coupling. So at this point, I wanted to just do a quick overview of some product choices you've got out there. my presentation so far has been pretty heavily weighted towards Outback and Schneider. That's not to say anything ill of Magnum. I just didn't have a lot of material from which to pirate slides and diagrams. But you know, all three of these brands have great solutions for DC and AC coupling. We carry all three. We carry charge controllers from other manufacturers that you can use in a DC coupled environment. I'm hesitant to include any information on which PV inverter manufacturers support AC coupling because that can change. I've got kind of a back of my mind list that I refer to on products that I've known to be approved and in good working order, but it's maybe not anything I want to commit to paper and you know, be responsible for a failed warranty claim. So you know, we've got lists we can maybe tell you about, and you can go do your homework on what's approved and what's not. If you're interested in an AC coupled solution, Magnum's got a great solution for their MS product and this GT500 microinverter, which gets you all of the benefits of AC coupling, as well as really good rapid shutdown and arc fault as well. From the Outback family, we've got the I've got here an FPR, which is the kind of pre-wired radiant solution with the GSLC DC coupled. For AC coupling, you'd want to use this GSLC down here with, again, a relay. Schneider Electric, kind of the same product across the board. In a DC coupled environment, you'd be looking at a MPPT 60 or an MPPT 80 charge controller, or you know, perhaps something from the Midnight family. In an AC coupled fashion, of course, you're using a PV inverter. You know, again, would counsel you to consult your manufacturer and make sure it's an approved application. So at this point, I ran through quite a lot, and we're closing in on the top of the hour, but we do have some time for question and answer, and I'll try to answer them as best I can.
All right, thank you, Josh. So we'll go ahead and start off the question and answer session now. So if you have a question, go ahead and submit it through the question pane located on your control panel. We'll try to answer as many questions as possible. At this point, if you'd like to, you can exit the webinar at any time. During or following the question and answer session, the survey will pop up in a new window once the webinar ends. Give us your feedback on the survey, and I will send you the presentation. So I'll first start off on a question here from Jerry. Outback stopped selling the breakers, relays. Sorry, Outback stopped selling the breakers. Relays are the best option available. Is there any comments to that, Josh?
They are the best option available. I don't have those part numbers handy, but Jerry, by all means, submit an email to us, to the tech team. That's techs@aeesolar.com, and we can recommend the right relay, you know, amperage basically that you'll need for that application.
All right. Here's one from James. Solar Edge DC coupling uses high voltage, so doesn't low voltage wiring cost issue?
So the question there is, you know, how do we compare the DC runs of a Solar Edge system versus the DC runs of an Outback or Schneider or Magnum DC coupled system? I didn't really touch on this too much, but for me, that's kind of apples and oranges. The DC voltage between the array and a Solar Edge inverter is going to be about 350 volts. That's going to be regulated by the optimizers once they turn on. They're going to seek to not transform, but they're going to seek to meet that 350 volts DC by doing a DC to DC conversion. That's a really efficient system for harvesting PV power. And then, of course, that storage system is going to couple the storage on the DC bus. So effectively, it's got, you know, a second channel, if you will, for the connection between the inverter and the at this point LG Chem only battery. So yeah, they've picked a high voltage DC. Those can be very that can be a very efficient way of harvesting that power. I'd say that's apples and oranges because while that application of course supports backup, it's not an extended backup type application. So you're limited to pretty low kW coming out of that inverter to support loads in backup. I believe they've raised it to 5 kW, but there's very little kind of surge capability in backup mode to support startup loads or, you know, turning motors, etc. So it's a bit apples and oranges when you compare something like a Magnum or an Outback or a Schneider. Those, you know, having an onboard transformer are going to provide a lot more, you know, surge or peak power than a SolarEdge will. The SolarEdge is a great application. I really recommend that for more of self-consumption, time of use, demand charges. The 3 that you see here, of course, we'll do those as well, but are probably going to be a better fit if you're looking at extended outages or you know, long islanding or off-grid usage. Great question. Thanks for pointing that out. It's a bit of a poor comparison, but you're exactly right. You know, the voltage between the array and the inverter will be much higher with a StoraEdge or SolarEdge solution.
Here's another one here from Bill. Aren't batteries L-A about 90 to 95% efficient?
Lead acid batteries. Bill, I'm gonna take your word for it. When I looked at my when we had that slide where we showed, you know, 1-stage conversion versus 2-stage conversion, I assumed 100% efficiency on those batteries. It's obviously not. You know, anytime you're moving around that kind of power, there's going to be losses to heat, losses to inefficiency. For the purposes of creating some simple math for comparing A versus B, because we were using a lead acid battery in both of those cases, I just said, let's keep it simple. Let's assume 100% efficiency. To your point, though, yes, not 100% efficient. And if we had applied that inefficiency, we wouldn't have seen numbers like, you know, 98 and 96 and 97%. We would have seen something like, you know, 85 and 92 and 93. But in comparing A versus B, if we control for that variable and we eliminate it, then you see the true impact of the trade-off there, which is 1-stage versus 2-stage conversion. So